this and the remaining few lectures, we will have problem solving sessions. So in today's session, we will consider problems that are based on theory of probability and random variables, which I covered during first few lectures, 4 or 5 lectures. So what I will do is I will consider a series of problems, explain what the problem is and suggest how it can be solved, and the presentation contains reasonably complete solutions. In some places there are hints, the solution is not complete, that at those places you have to complete the steps that still remain at the end of that. So we will start with some problem. These problems are not graded in any specific order of complexity or difficulty. So let us see how it goes. So first problem, a coin is tossed 10 times. Probability of obtaining head on any given trial is 0.4. Now find the probability that head shows up no less than 5 times and no more than 3 times. So we need to model now, and when we toss the coin there are 2 possible outcomes. That is a Bernoulli trial, and the probability of getting head, which we may call as event of success, remains constant, and these trials are independent. So we can model this tossing of coins as a repeated Bernoulli trials, and we know that number of successes in k trials follows the binomial distribution. Probability of x equal to k is n c k p to the power of k 1 minus p to the power n minus k, where k runs from 1 to n. Now we are given that in this example n is 10 because there are n trials and probability of success is 0.4, and the event that we are asking is, we are considering is head shows up no less than 5 times and no more than 3 times. That would mean we are looking at the probability that x is greater than or equal to 5 or less than or equal to greater than or equal to 3 or less than or equal to 5. So we have to sum this probability from 3 to 5. So if we do that, there will be terms corresponding to k equal to 3, 4 and 5, there are 3 terms, and upon evaluating this we get the number 0.3547. So that is the answer to this problem. Next we will consider a random variable x, which is a Poisson random variable, such that probability of x equal to k is e raised to minus a to the power of k divided by k factorial, with parameter a given to be 1. Now I define a new function, a function of this random variable, that is defined as y is equal to minimum of x comma 4. Now the question is, how do we characterize y? Now y is a discrete random variable. Poisson random variable is a discrete random variable with countably infinite sample space, whereas y will be a discrete random variable with finite sample space, because it assumes only 5 possible values 0, 1, 2, 3, 4, these are the possible values. If we get, for example, x equal to 5, then according to this transformation y will assume value of 4. So now therefore what are the probabilities associated with these outcomes? Y equal to 0 is probability of x equal to 0, there is exponential of minus 1. Probability of y equal to 1 is probability of x equal to 1. Similarly y equal to 2 is Poisson, x equal to 3 is Poisson. Now y equal to 4 can happen when outcome is 4, 5, 6, 7, 8 for x. So that is 1 minus probability of x less than or equal to 3. So that probability will be 0.190. So if you add all this, they will add to 1. So this is the solution to the given problem. So we have now obtained the probability mass function. We could evaluate the characteristic function from which we can get moments, etc. So the characteristic function is expected value of exponential I omega y, and this is a discrete random variable assuming 5 values. So if you substitute that, we get the characteristic function to be given by this. Now if you differentiate this with respect to omega and put omega equal to 0, you will be able to find out the mean and so on and so forth. So once the characteristic function is known, we know we can easily evaluate the moments. Now some simple exercises related to properties of a normal random variable. when I discussed these aspects during the lecture, I left them as exercises. Now is the time to look at them. Let x be a normal random variable with parameters m and sigma. Now how do we show that expected value of x is m and variance of x is sigma square, and characteristic function is given by this. So this exercise is simply an exercise in evaluating these integrals, so that you become familiar with the methods of evaluating these integrals. So let us start with expected value of x. So this is 1 by square root of 2 pi sigma minus infinity to infinity x exponential of this into dx. So what I do here, x I write it as m plus x minus m. So the first term m into this integral is taken outside, and this integral accepting this term m is 1 because area under probability density function is 1, that is one of the axioms of probability, and the remaining term is x minus m by sigma into this. Now I substitute x minus m by sigma as u, and I will get dx as sigma du, and we substitute that into the second integral. Now you can see that this is an odd function under symmetric limits, therefore this value is 0. So I get the required result that expected value of x is m. Now how do we show that variance is, how do we evaluate the variance? So variance is expected value of x minus m whole square. So this is the expression that we need to evaluate. Now what we could do is, we can begin by the result that area under the probability density function is 1. This I have shown during the lecture. Now we can rewrite this as integral minus infinity to infinity exponential of this function dx is square root 2 pi sigma. Now if I differentiate this with respect to sigma, I will get sigma is residing here, I will get this term into exponential is equal to square root 2 pi. Now if I rearrange, say sigma, rearrange these terms, I will get 1 by square root of 2 pi sigma x minus m whole square exponential this dx is equal to sigma square. So this is a simple way of showing that variance of a Gaussian random variable is sigma square. Now characteristic function is again in terms of m and sigma, as we already know, but how do we show that this is correct? So definition of characteristic function is expected value of exponent of I omega x, exponential of I omega x, and this is the integral. So now we begin by making the substitution x minus m by sigma is equal to u, and upon this substitution the exponent becomes u square by 2, and there will be slight rearrangement of these terms, and terms not containing u can be pulled outside, and this I omega sigma u can be taken inside the exponent, and this can be rearranged so that we get a proper square of an integral and a remaining term. The remaining term is free from the variable of integration u, therefore it can be pulled outside, and what remains would be the area under the Gaussian probability density function, which is 1. So we get characteristic function to be equal to 1. Some more exercises of a similar kind. Let x be a Rayleigh random variable with probability density function as given here. So we are asked to find probability that x takes value greater than the mode of the random variable, x takes value greater than the mean, and x takes value greater than mean plus 1 standard deviation. This again is an exercise that would familiarize with integration processes involved in characterizing random variables. So we can sketch this random variable for the given parameters, and blue line is the Rayleigh probability density function, and mode is a point where the probability density function peaks, so that is dpx by dx is equal to 0 at this point, and mean and mean plus sigma are to be evaluated, we still do not know where they are. So we will do that. Now first and foremost we can verify whether this is a valid probability density function. So for that the area under the probability density function should be equal to 1. So we can check that. So to do that I substitute x square by 8 is equal to t and make this substitution, and we can verify that area under the density function is indeed equal to 1. Now what is the probability distribution function? It is integral 0 to x px of x pu of u du. So, if you do this again, I make the substitution u square by 8 is equal to t and carry out this simple integration, I get the probability distribution function. Now, we are asked to evaluate probability that x takes value greater than the mode. First, we have to therefore determine what is the mode. The mode by definition is the point at which dpx by dx is equal to 0 at that value of x equal to x star. So, if I do this exercise, if I differentiate the probability density function and equate it to 0, I get x equal to 2. So, the mode of this density function is 2. Now, what is probability x greater than mode? It is probability of x greater than 2 or 1 minus p of x less than or equal to 2, and we have already determined the probability density function. So, we get a probability distribution function. So, we get the number 0.6065. Now, the next is what is probability that x is greater than the mean. So, to answer that, we have to first find the mean. Mean of x is x square by 4 integral 0 to infinity x square by 4 exponential minus x square by 8 dx. Now, how do we evaluate this? We can consider a random variable u which has 0 mean and standard deviation as 2, and we know that the integral minus infinity to infinity u square divided by square root of 2 pi 2 exponential minus u square by 8 du is 4. Therefore, by this it will follow that we are interested in this integral, and this is actually 0 to infinity, whereas this is from minus infinity to plus infinity, but the variable of integration is this integrand is a even function. Therefore, I can write it as 2 into this integral. Using that, I get the required integral to be 4 into square root of 2 pi. Therefore, expected value of x is square root of 2 pi. Now, we also need to find out the standard deviation. So, expected value of x square is x cube by 4 exponential minus x square by 8 dx. So, I will write it as x into x square and make the substitution x square by 8. So, if we follow through these steps and we get variance to be this. So, probability that x is greater than or equal to 2, which is probability that x is greater than mode, I get 0.6065, and mean is found to be this, and therefore, probability x greater than mean is this number. Mean plus standard deviation is found out to be this, therefore, probability of x greater than mean plus standard deviation is this. So, these are the required numbers that we are looking for in this problem. We consider in the next problem the probability density function of a random variable x is given to be px of x is a sin pi x, where x varies from 0 to 1. The questions that we need to answer is how to find a, and then if I define y is equal to cos pi x, we are asked to find the mean and variance of y, and we have to repeat this exercise if y is now defined as y is equal to mod of cos pi x. So, how does the probability density function look like? Px of x is a sin pi x, x taking value from 0 to 1. The shape of the probability density function looks like this shown here, and x takes value from 0 to 1. We have not yet found the value of a that we need to find out, so that the area under the probability density function is 1. And how does cos pi x look like? Over the range of interest, the cos pi x function is this, and mod of cos pi x is this. So, in this portion cos pi x and mod of cos pi x overlap, therefore, we see only the red line here, which is mod of cos pi x, and the blue line is cos pi x, which runs along this line. How do we find a? The area under the probability density function should be equal to 1, and if you do quickly this integration, we get a equal to pi by 2. So, the probability density function is pi by 2 sin pi x, where x runs from 0 to 1. Now, consider y is equal to cos pi x. What is expected value of y? It is cos pi x, pi by 2 sin pi x dx. So, this we can write it as half of sin 2 pi x, and once we integrate we can show that the mean is 0. What is mean square value? integral of cos square pi x pi by 2 sin pi x dx, and if you make the substitution cos pi x is equal to t and carry out this integration, we get the mean square value to be 1 by 3. Since mean is 0, the mean square value itself is the variance. Now, how about modulus of cos pi x? So, y is modulus of cos pi x. So, expected value of y is 0 to 1 modulus cos pi x pi by 2 sin pi x dx. Now, we can split this integral. If you go back to this function, we see between 0 to 0.5 cos pi x is positive, and from 0.5 to 1 the function is negative. So, once you take modulus, we can carry out the integration from 0 to half and half to 1 along this. So, accordingly we can rewrite this as 0 to half cos pi x pi by 2 sin pi x dx and half to 1 cos pi x pi by 2 sin pi x dx. So, this integration can be carried out, and we can show that the expected value of y is 1 by 4. Now, how about mean square value? This 0 to 1 cos square pi x px of x dx, and this is same as expected value of y square that we obtained in the previous example, that is 1 by 3. So, from this I can get the variance to be the mean square value minus square of the mean, and that turns out to be this number 13 by 48. Now, let us consider x to be a random variable which is exponentially distributed with parameter lambda. X takes value from 0 to infinity. So, the question that we need to answer is determine the characteristic function and hence determine the mean and standard deviation of x, and we need to show that the shaded area in the figure, that is here this shaded area, is equal to the mean of the random variable. Mind you, this is probability distribution function, and what we are asking is area under 1 minus px of x dx as shown here through the shaded region is actually the mean of this random variable. So, the probability distribution function is given to be 1 minus e raised to minus lambda x. Probability density function is lambda exponential minus lambda x. The characteristic function is defined as phi x of omega is expected value of exponential I omega x. So, this is 0 to infinity exponential I omega x lambda exponential minus lambda x dx, and this has this form, and this can be integrated, and once we put the limits infinity, e raised to minus lambda x, this can, the numerator can be viewed as e raised to minus lambda x into e raised to I omega minus I omega x. E raised to minus I omega x amplitude is bounded between plus and minus 1, because basically that is cos omega x plus I sin omega x. So, that harmonic function is multiplied by e raised to minus lambda x, and as x tends to infinity, the real part e raised to minus lambda x goes to 0, therefore, the numerator goes to 0. So, we get the characteristic function to be lambda divided by lambda minus I omega. Now, how is the characteristic function related to the moments? We have already shown expected value of x to the power of n is 1 by I to the power of n, and the nth derivative of characteristic function evaluated at omega equal to 0. So, now we can use this and evaluate the mean and variance, mean square value and variance as is required in this problem. So, phi x of omega is this, and differentiation of that gives to this, and at omega equal to 0, and 1 by I of that is 1 by lambda, which is the mean of exponential random variable. Similarly, the mean square value can be shown to be 2 by lambda square, and consequently the variance becomes 1 by lambda square. Now, how about this shaded area? This shaded area is nothing but 0 to infinity 1 minus px of x dx is exponential minus lambda x dx, which is 1 by lambda, which is actually the mean. So, it can quickly be verified. But this result has more general validity in the sense, if we consider x to be a non-negative random variable, that is probability of x less than or equal to 0 is 0, we can show that the shaded area in the figure, that is in the next slide, this is now the arbitrary probability distribution function of a non-negative random variable, is not necessarily exponential. So, the general result is this shaded region, that is a red area here, this area is equal to the mean of the random variable. So, how do we show that? What we need to show is expected value of x is 0 to infinity x of the probability density function dx. This is a definition of expected value, but it turns out that this integral is also equal to 0 to infinity 1 minus px of x dx. So, how do we show that? You consider this expected value of x is x px of x dx, and px of x is derivative of the probability distribution function. Therefore, I can write it as x px prime of x dx, and I can write this as 1 minus px of x prime. So, the prime of derivative of 1 is 0, therefore, I can write this without making any error, and there is a minus sign to allow for this negative sign that we have introduced. Now, we can integrate by parts. So, this is x 1 minus px of x dx 0 from 0 to infinity plus 0 to infinity 1 minus px of x dx. Now, this the claim is that this quantity, this is second integral, is actually equal to the mean of the random variable. So, if that is true, then the first term should be equal to 0. Now, if we consider the lower limit x going to 0, we see that since x of x is a non-negative random variable, px of 0 is 0, therefore, the lower limit goes to 0. The upper limit extending to infinity, what happens to this is a question. Now, since we are assuming that the mean is finite, it means that limit k tending to infinity of k to infinity x px of dx is 0, and since k into k to infinity px of dx is less than or equal to k to infinity x px of dx, it follows that limit of k tending to infinity k into this function is 0, and consequently we show that the expected value of the random variable is indeed the shaded area that we showed in the figure. The next example is again with an exponential random variable. So, x is a exponential random variable with parameter lambda, and lambda is given to be equal to 2, and we define z as maximum of x comma 2. The question is determine the probability density function of z and comment on what kind of random variable is z. Subsequently, we are asked to determine the characteristic function and hence evaluate the mean of z. So, how do we do this? Z is maximum of x comma 2 implies that Pz of z is from x equal to 0 to 2, it follows the exponential distribution. So, lambda exponential minus lambda z, u is the step function, u of 0 minus u of 2 plus it is then a Dirac delta function centered at z equal to 2 with probability of x greater than or equal to 2. Now, so z becomes a mixed random variable, and we can show that the characteristic function is given by this. We can evaluate these integrals and show that the characteristic function is this. So, this simplification follows, and you can verify that these steps are acceptable. The next problem, we consider two random variables x and y, and we assume that they are independent standard normal random variables, and I define z as modulus of 2x minus 3y. The question is find mean of z. Now, to solve this problem, what we do is we introduce a random variable u, which is 2x minus 3y. Expected value of u is 0 because mean of x and mean of y are given to be 0. So, what is mean square value? It is 4 into x square plus 9 into y square minus 12 into expected xy, and this is 0. Therefore, I get 9 plus 4 is 13 because mean square value of x and y are unity. So, probability density function of u is indeed another normal random variable with this density function, where standard deviation is square root of 13. So, thus the given problem can be viewed as finding expected value of a modulus of a Gaussian random variable, and so this is the probability density function, and modulus of u is expected value of modulus of u is minus infinity to plus infinity mod u into the density function. This can be written as 2 into this area 0 to infinity u by square root 2 pi sigma etcetera du. Now, if you substitute now u square by 2 sigma square is equal to t and carry out this integration, we can show that the expected value of u turns out to be this number 2.8767. In our discussion we came across Cauchy random variables, and one of the properties that Cauchy random variable satisfies is that if x is a Cauchy random variable, 1 by x is also a Cauchy random variable. So, how do we prove this? So, x is Cauchy means the probability density function is 1 by pi divided by 1 plus x square, where x takes values from minus infinity to plus infinity. Now, we define y is equal to 1 by x, and therefore, the gradient is minus 1 by x square, that is minus y square. So, using rules of transformation of random variables, Py of y is Px evaluated at x equal to 1 by y divided by the absolute value of the gradient, which is y square, and Px of 1 by y is 1 divided by pi divided by 1 plus 1 by y square into 1 by y square, and you simplify, you get that y is also a Cauchy random variable. Now, a few examples involving transformations on a Gaussian random variable. So, let x be a standard normal random variable. By standard normal random variable we mean mean of x is 0 and standard deviation is 1, and we are asked to find the probability density function of say y equal to x square, y is equal to mod x, y is equal to signum of x, y is equal to minimum of x comma x square. So, how do we tackle these problems? So, we will begin with the definition of Px of x. If x is normally distributed with mean 0 and standard deviation 1, the density function is 1 by square root of 2 pi exponential minus x square by 2, where x is from minus infinity to plus infinity. Y equal to x square means x can take two values plus minus square root of y. Now, dy by dx is 2x, therefore, that is equal to plus minus 2 into square root of y. Now, therefore, Py of y is Px of x evaluated at the two possible roots, namely plus square root of y and minus square root of y divided by the gradient, which is 2 into square root of y. Now, we know Px of x is Gaussian, and if you substitute there is a, since we are having x square here, square root plus minus square root of y will translate to the same number. So, we get Py of y to be this function. Now, how about y equal to mod x? Probability of y less than or equal to y is probability of mod x less than or equal to y. That would mean x takes values between x, the probability of y less than or equal to y is same as probability of x greater than minus y less than or equal to y. So, this is nothing but probability of x less than or equal to y minus probability of x less than or equal to minus y. So, by denoting the probability distribution using capital phi, we write this as phi of y minus phi of minus y, and upon differentiation I get 2 into phi of y, where y is greater than or equal to 0. So, the probability distribution function of mod x is shown here. Just for verification, a simulation was also performed with 10,000 samples. The blue line is the simulation and red line is the theoretical result. Now, how about y is equal to signum of x? Signum of x, the meaning of that is y is equal to 1 if x is greater than 0, y will be minus 1 if x is less than or equal to 0, and y will be 0 if x is equal to 0. That means signum of x is a function, this is plus 1, this is minus 1. Therefore, y is a discrete random variable that takes values 1, minus 1 and 0, but since x is a continuous random variable, probability of x equal to 0 is 0. Therefore, I get the probability density function of y to be direct delta of y equal to 1 into probability of x greater than 0 plus direct delta y equal to y plus 1 probability of x less than or equal to 0. So, with that I get the density function to be half of Dirac delta y minus 1 plus Dirac delta y plus 1. How about the function minimum of x comma x square? So, probability density distribution of y is probability of y less than or equal to y, that is probability of x square less than or equal to y if y belongs to 0 to 1, or probability of x less than or equal to y if y does not belong to 0 to 1. That means, if we plot this function here, this blue line is y equal to x and this red line is x square. So, we are taking minimum of these two values, and in this region between 0 to 1 red line is smaller than the blue, and outside red line takes the greater values. So, therefore, we write probability of x square less than or equal to y for y lying between 0 to 1 and probability of x less than or equal to y for y outside this region. So, using that I get probability density function to be given by these two functions. Now, a slightly complicated problem. Let x and y be a standard normal random variables. We are asked to find the probability density function of z, which is sum of mod x and mod y. So, what we do is we define u to be mod x and v to be mod y, and we have obtained the probability density function of mod x and mod y just now. So, the probability density function of mod x is given by this, and which is u, and probability density function of v is given by this. Since x and y are independent, we are assuming that x and y are independent, u and v would also be independent. So, we have now z is equal to u plus v, and we are asked to find probability density function of z, and as we know, this is given by the convolution of probability density of u and v, which is given by this. So, that would mean this integral is in terms of pu of u, this is this, and in terms of pv of v evaluated z minus u, I get these terms. So, a slight rearrangement and ensuring that the exponent is expressed as a perfect square, and rearranging these terms, we need to manipulate some of these expressions, and we can show that there are several substitutions that we need to make, so that within the exponent we get a perfect square, and then we are able to evaluate this using known results. If we do that, we get the probability density function of z to be this. So, this is a fairly involved exercise. You are encouraged to go through these steps and see if they are correct. Now, the plot of this function Pz of z is shown here, and it was numerically verified that area under this function is 1. Now, let us consider two random variables x and y. The probability density function is a constant wherever x and y lie within a circle, that is square root of x square plus y square is less than or equal to 2, otherwise it is 0. So, the problem on hand consists of finding this constant c, then finding marginal probability density functions of x and y, and to verify if x and y are independent. Following this, there is another subsection here. Select a point B inside the circular region square root x square plus y square less than or equal to 2, and let r and r comma theta be the polar coordinates of B. We are asked to determine the joint PDF of r and theta, marginal probability density function of r and theta, and we need to verify if r and theta are independent. Now, we have the joint density function Pxy of x comma y is a constant for x and y belonging to this region, square root x square plus y square is less than or equal to 2. So, the area under this density function should be equal to 1, that would mean the double integral over the region square root x square plus y square less than or equal to 2 c dx dy must be equal to 1, and from that condition we get this should be equal to 1 and I get c to be equal to 1 by 4 pi. Now, how do we evaluate the marginal density Px of x? So, we need to integrate, we need to select this is x, this is y, we need to integrate from this point to this point. So, this if this is x, this will be square root of minus 4 minus x square and this will be square root of 4 minus of square root 4 minus x square plus of square root 4 minus x square 1 by 2 pi dy, and we get this density function. Py of y, by the same token we need to select a line like this and integrate from these 2 points, and accordingly we get this function. Now, if I multiply Px of x and Py of y, you can verify that their product does not lead to the function which is a constant, that is 1 by 4 pi. From this we can conclude that x and y are not independent. So, this is a plot of probability density function of theta, that is this function Px of x is 1 by square root of 2 pi 4 minus x square. This looks like this. The next part of the question is, within the circular region we select this point r, select this point, and this is the coordinates r and theta. So, the coordinates of this is x comma r, which is x is r cos theta, y is r sin theta. Now, we are asked to find the joint density function between r and phi. Pxy, joint density of x and y is given to be 1 by 4 pi whenever x and y lie within this circle, within this circle. So, therefore, r takes values from 0 to 2 and theta takes values from 0 to 2 pi, and if I integrate this over 0 to 2 pi, I get Pr of r to be r by 2 for 0 to r varying from 0 to 2, and P theta of theta to be 1 by 2 pi where theta varies from 0 to 2 pi. Now, if I multiply these two, Pr of r and P theta of theta, I get P r theta of r comma theta, which is r by 4 pi, which is nothing but r by 2 into 1 by 2 pi. Consequently, we reach the conclusion that r and theta are independent. The next problem is, we consider a sequence of random variables xi with a common density function which is an exponential density function. We define y to be I equal to 1 to xi, and the problem on hand consists of determining the probability density function of y for lambda equal to 2 and n equal to 10. Now, there are two possible ways to evaluate this. I will give hints on how to solve this. One is we start by finding x1 plus x2 by convolving the probability density function of x1 and x2, and suppose if this is say y1, then we convolve this resulting density function into with x3, that leads to y2, convolve with x4, that leads to y4, and so on and so forth. We can show that at every step there will be sums of exponentials that will emerge in probability density functions, and this process can easily be carried out. Other approach is to interpret the exponential distribution as a model for interarrival time between Poisson points and consider the event Py of y dy, which is nothing but probability that exactly n minus 1 points occur in 0 to y and one event in y to y plus dy, and if you use this we can get this density function, and this density function is known as Erlang probability density function, and this is a special case of the gamma density function where n is an integer. So, this is how this function looks like. Next we consider a well known problem known as Buffon's needle problem. This problem is of historical interest. I will clarify what that means. So, here a set of n parallel lines equidistant from each other is drawn on a plane, that is here in this figure. The lines are at a distance L from each other. So, these vertical lines here are equally spaced and the distance is L. Now, we select a needle of length small l, that this needle is of length small l, which this length is smaller than capital L, and what we do is we place this needle randomly on this plane and we consider the event whether this needle intersects any of these lines. So, we want to find out the probability that the needle would intersect one of the lines. So, what we do is we consider a position, a situation where needle has landed between two lines, and consider the midpoint of the needle and measure the midpoint of the needle, the distance of this midpoint to the nearest vertical line to the left, call it as x, and this angle as phi. Now, since the needle is being placed on this plane randomly, we can infer that x is uniformly distributed between 0 to L by 2, and similarly this angle phi is uniformly distributed between 0 to pi by 2, and x and phi are independent. Now, so what is the event that needle intersects the line? Needle will intersect the line if, when x is less than or equal to sin phi. That means this shaded region A is the in the phi x plane, capital omega is this rectangle which is a sample space, and this blue shaded region is the event, the subset of sample space which is favorable to the event that we are looking for. And if we do that calculations, we find that probability of x is less than or equal to sin phi is 2L by pi L. And consequently, you know this probability is a function of pi. So, historically this experiment was used to estimate value of pi. So, you can toss this needle and actually measure the probability that using relative frequency approach, how many times this needle intersects the vertical line, and based on that once you get that estimate of probability, you can go back to this formula and get an estimate of pi. So, it is in this context that this problem has some historical significance. Let us consider now in the next problem x to be a normal random variable with mean m and standard deviation sigma. The first part of this exercise is to show that expected value of x to the power of n is m into expected value of x to the power of n minus 1 plus n minus 1 sigma square x n minus 2. Now, we define x and y to be two normal random variables is the next part of the problem, where the mean of x and y is 1 2 and covariance is 4 0 0 9, that means x and y are independent. Now, I introduce two new random variables u and v through this relation. U is 2 plus 4x plus 10xy and v is 1 plus 2xy plus 6y square. The problem is to find the mean and covariance of u and v. So, this is a fairly straightforward exercise which will tell you how to manipulate moments of Gaussian random variables. So, what we could do is we could remove the mean from x and y and recast the expression for u and v. That is, what we do is we begin by noticing that x and y are uncorrelated. and therefore they are also independent because they are uncorrelated. Now we introduce new random variables, x1 is x minus 1 by 2, which is the standard deviation of x1, that is x, and x2 is y minus 2, which is the mean, divided by 3, which is standard deviation of y. So consequently we get expected value of x1 is 0 and variance of x1 will be unity. Then we recast u and v in terms of x1 and x2. For x I will write it as 2x1 plus 1, and for y I will write 3x2 plus 2, and simplify these expressions. I will get now u and v in terms of x1 and x2, which are easy to manipulate. Mean is 0, standard deviation is 1, they are independent. Now consequently we can find, for example, we get these two as the expression for u and v. Now expected value of u is, we can simply operate on this will be 26, because expected value of x1 x2 are 0 and x1 and x2 are uncorrelated, therefore this is 26. Expected value of v is, again we operate on this expression, expected value of x1 is 0, x2 is 0, expected value of x1 x2 is 0, but we have this expected value of x2 square, which is unity, therefore the answer will be 29 plus 54, which is 83. Next I define u1 to be u minus 26, which is u1 is a random variable with 0 mean and v1 is v minus 83. I get these expressions, and this will be helpful in finding variance and covariance of u and v. So sigma u square will be expected value of u1 square, which is square of this. So similarly sigma v square will be expected value of v1 square, which is this, and covariance of u and v will be in this form. So when you do it, for instance, you will get here say terms like expected value of x1 square, x2 square, or x1 cube and x2 square, etc. So to evaluate that, you need to use the result that you need to show as a first part of this exercise. That this I leave it as an exercise. You can use the characteristic function and show this. Now another problem on sequence of random variables. We consider x1, x2, xn to be an IID sequence of random variables with common probability distribution function px of x. Now what we will do is we will arrange x1, x2, xn in an increasing order, and we denote the lowest value as x subscript 1 colon n, next one is x2 colon n, and so on and so forth, x n colon n. Now the problem on hand is to find the probability distribution function of the rth member in this ordered list. So where r runs from 1 to n. Now the first one here, x1 of n, is nothing but minimum of x1, x2, xn. Similarly the last one is maximum. We have already determined the probability distribution of the minimum and maximum. Now what is being asked is, in this ordered list, can you pick any number r, rth candidate in this ordered list, and what is the probability distribution function of that. Now to answer this question, we consider a trial in which a sample of x1, x2, xn is observed. We define success as the event xj is less than or equal to x for a specified value of x. Now then define mn of x is number of elements in the sample for which values xj is less than or equal to x. Now mn of x is a random variable following binomial distribution with p is equal to probability of xj less than or equal to x, which is px of x, and following that I get probability of mn of x is equal to k is the binomial distribution nck p to the power of k 1 minus p n minus k, k running from 1 to n. Probability of mn of x less than or equal to r is given by this summation, and I get mn of x less than or equal to r is this, Now from this, if we consider the event x Rn less than or equal to x, that means the rth candidate in the ordered list has a value less than or equal to x, it would mean r or more elements have values greater than x. Therefore, this is nothing but Mn of x is greater than or equal to r. Now therefore, now we have characterized Mn of x as a random variable, therefore I would be able to derive this probability density function for the rth member in the ordered list. Now Px of x, in this of course you can use the specified density function, it could be Gaussian, normal, Rayleigh, whatever, and you will be able to proceed further in simplifying this expression moment you know the details of Px of x. So with this we will conclude this session of problem solving. So in this session we have basically considered problems involving theory of probability and random variables. So in the next part we will consider problems involving random processes. So we will conclude this lecture at this point.